Alright, the goal of this video is to get ready for our test on average value theorem, mean value theorem, fundamental theorem of calculus. And so we're starting with a warm-up. This is in your packet. I think it's page 34. And we want to make sure that we understand how to find the average rate of change, average rate of velocity, and what all of these things mean. So we're going to start, and notice it says that the answers may be used multiple times. So my suggestion would be to start with the right-hand side and figure out what those things indicate. So in letter A, if we actually think of evaluating that, if we find the antiderivative of a position function, I'm not sure what that takes us back to, so we'll hold off on that one. That's probably one of our distractors. If we find the antiderivative of velocity function, we will get position back, so that this would be equal to s of b minus s of a over b minus a. So this is equal to average velocity by definition, change in position over change in time. If we find the antiderivative of acceleration, we'll get the velocity function back, so that would be v of b minus v of a over b minus a, so that would be change in velocity over change in time. This would give me the average acceleration. E is the same thing as b, so that would, these two are the same. We probably should keep that in mind. C is the same thing as F, so we want to keep that in mind, that these represent the same thing. And A of B minus A of A over B minus A would give me, that would give me average, that would give me the average rate of change of acceleration. Alright, so let's see what we got here. First one says average rate of change of position. Well, the average rate of change of position is equal to average velocity. So average rate of change of position would be average rate of change of position, since it's average velocity, would be b, and it would be e. Those two are the same. The average rate of change, or the slope, think of it like that, slope of velocity would equal to average acceleration, and we said the average acceleration was c and f. The average rate of change of acceleration was letter G. The average value of position, so that tells me basically to use the average value formula on the position function, which is letter A. So there's my average value formula used on the position function, 1 over b minus a, and there's my position function. The average value of velocity tells me to use the average value formula on the velocity function. So that's telling me to do 1 over b minus a of v of t dt. And that's the same thing as average velocity. So that's equal to b and e. So these two are the same. Average value of acceleration tells me to use the average value formula on acceleration. So that's clearly c, which is the same thing as f. So 2 and 6 are telling you to do the same thing. And that I'm using different language so that you can see which of these are the same, which of these are different. Average velocity is the same thing as the average value of velocity, so that matches up with 1 and 5, and that's equal to b and e. So make sure you understand the average velocity is asking you to find the average value of velocity. In other words, it's simply change in position over change in time. Average acceleration is the same thing as asking you the average value of acceleration. So that's C and F. Number 9 and number 10 are easy. Number 9, we're looking for change in position over change in time, which is going to be B and E. And number 10, we're looking for change in velocity over change in time, so that's going to be C and F. All right, so take some time to really study this and make sure you understand the words and which ones are the same, which ones are different, and what they're really asking you. You're going to want to take some time to review the Fundamental Theorem of Calculus Part 2. If you have any questions on those, you're welcome to come and see me. These are the pages out of the book. I'm going to look at that in the actual test review. You should have a copy of the topics that are going to be included on the test and where to find those. The only thing, well, it's already there. Make sure that you spend some time focusing on AP problems, and it's not 1 through 3, it's number 1 and 3. Those are the problems that were assigned to you after your exam that you need to study, because those concepts or problems very similar to those will appear on your test. This is a page out of your textbook on just using the fundamental theorem of calculus. So in other words, the antiderivative of from a to b of f of x dx. The fundamental theorem of calculus says you find the original function, big F at b, evaluated at b, minus big F evaluated at a. You need to know the integral properties. Make sure that you spend some time going back through this page in your textbook for the examples of what we did there. Again, number 40, this is from your textbook. I'm just kind of reviewing some of the homework that we had. This was before the exam, so you're going to want to take time to go back and make sure you understand your integral properties and how to use those. This is an initial condition problem. An initial condition problem is one in which, for example, in this case, if we want to determine the velocity at 5 seconds, we have the acceleration given. dv dt is acceleration. I think this might be in your packet. So we're going to need to find the antiderivative, so of v of t dt from, well, we can just find the general antiderivative, and then we're going to end up with, I'm sorry, a of t. We're finding the antiderivative of acceleration because that's what was given. So we're going to get a velocity function. We're going to have a plus c, and the big idea here is that at 5 seconds the velocity is negative 12, so you have 5 negative 12, and that's what allows you to solve for c. So that's what I'm talking about with an initial condition problem, is where you can actually go back and solve for the value of c. And then you have a variety of questions about that. This is problem number 3 from the AP problems. This looks at initial conditions again. Notice it says where you are. So this is the important part I'm trying to focus on. Where you are at any given time is a function of where you started and where you've gone from your starting point. So what this is really talking about is position. It's not talking about total distance traveled. It's talking about the position of a particle. Position is relative to where did you actually start traveling from. When you accumulate at a variable rate, you need to use this definite integral to get your net accumulation. And again, that's going to give you change in position. We're not talking about distance traveled. We're talking about position. An important idea of accumulation: what I have now is equal to what I started with plus what I've accumulated since I started. So mathematically it can be expressed this way. F of b is equal to f of a. In other words, where I started, how much area I had collected at the time of a. Then I'm going to collect more area from a to b, and that will tell me my final or terminal position. not distance traveled, but my position. Here's the average value theorem homework, 1 over b minus a from a to b of f of x dx. Remember, this is the change in time. Anytime you're finding an average, remember we talked about that you add up all your stuff and you divide by the number of stuffs. So in this case, the integral part is adding up. That's my accumulator. It's adding up all my stuff. And the 1 over b minus a, that's dividing by my number of stuffs. And here's the actual test review that you hopefully have already taken a look at. So I'm going to run through these quickly because the answers I'm going to show you. Everything here is important. In number 1, you're looking at finding the derivative of a definite integral. So that's the fundamental, not that you have to know what it's called, but it's the fundamental theorem of calculus part 2. And when I taught you this, I told you there are basically 3 easy steps. Number 1, you take out the t. In other words, that's the dummy variable. Number 2, you put in the new function, and the new function is that guy. And number 3, you multiply by the derivative of the new function, and there's your chain rule. Now, there is a video that really explains why we're doing what we do, because we did the theory behind it, and then we just said, okay, here's a shortcut to doing this. So, for example, in 1a, if I'm trying to find the derivative of this definite integral, I don't really have to find the antiderivative of secant squared. I just secant, take out the t, so there's my dummy variable gone, put in the new function, which is 2x cubed, and multiply by the derivative of the new function. So the derivative of 2x cubed is 6x squared. And I could rewrite that and put the 6x squared in front if I wanted to. One more look at that. Let's look at letter B, because you'll notice in letter B that the bounds are out of order. So this is the same thing as the derivative of, if I want my constant to be initial, that would be the same thing. If I'm going to change the bounds, I change the sign. That goes 7 e to the x t squared plus 5t dt. Alright, so now when I find the derivative, there's my negative. Take out both t's. Put in the new function, which my new function is e to the x, so it goes here and here. So there's e to the x, and then multiply by the derivative of the new function. The derivative of e to the x is e to the x, so I get negative e to the 2x, not x squared. X, when you have a power to a power, you multiply the powers, minus 5e to the x multiplied by e to the x. And so that's the same thing as negative e to the 3x, keep the base and add the exponents, minus 5e to the 2x, keep the base and add the exponents. Again, the answers are shown on the next page, and I will take a look at that in a second. Number 2 is more of the same. You're finding the derivative, your fundamental theorem of calculus part 2. Let's take a look at number 3. Because number 3, instead of having a numerical lower bound, we have a variable lower bound and a variable upper bound. We're still doing the fundamental theorem of calculus part 2. But this time we're going to take out the t. We're going to have to do it twice, once for the upper bound and once for the lower bound. So take out the t, put in the new function, multiply by the derivative of the new function. Remember, the derivative of an exponential function is the function times the ln of the base times the derivative of the power, which in this case is just 1. Okay, so that takes care of the upper bound. So take out the t, put in the new function, multiply by the derivative of the new function. So that takes care of the upper bound, minus lower bound. Take out the t, put in the new function, 2 plus sine 2x, multiply by the derivative of the new function. The derivative of 2 is 0. The derivative of sine 2x, the derivative of sine is cosine 2x times the derivative, which is cosine 2 cosine 2x. And that's all we can do with that. Number 4, we're finding the definite integral. So we're going to find the antiderivative of secant squared. Remember, you ask yourself, who has a derivative of secant squared? And that's going to be tangent x. So I find the antiderivative evaluated from lower bound to upper bound. So that's tangent of pi over 4 minus tangent of 0. Tangent of pi over 4, that's 45 degrees, so that's going to be 1. The tangent of 0, remember, tangent is sine over cosine, and the sine of 0 is 0, so I get 1 minus 0, which is 1. D, the absolute value functions can be dangerous. The easiest way is to sketch the graph. The vertex of this absolute value function is going to be at 1/2, so there's 1 and there's a half. We're going from 0 to 2. So basically I want to evaluate this function at 0 when x is 0. When x is 0, y is 1. So I'm going to find the area of this little baby triangle right here. So that's a half a unit by 1. So a half of a half is a fourth. So this little triangle right here, the area is 1/4. Now I have a triangle. I'm going to stop at 2 when I substitute 2 in here. 2 times 2 is 4, minus 1 is 3, so 2, 3. So I have 3 units of height, and then my half from 1/2 to 2, that would be 1.5. Did I have that right? Let's see. I'm at half a unit here. 1.5 would be 1. Okay, so 1.5. And 3 times 1.5 gives me 4.5. And half of 4.5 gives me 2.25. So I'm going to add 2 1/4 to 1/4, which gives me 2 1/2. So the key when you're finding, when you're evaluating definite integrals of absolute value functions, you want to sketch the graph, and I think the answer, let's take a look back here, probably did a much cleaner job of doing that. Okay, so you can see I did the same thing on number 4D. I graphed the absolute value function and I found the area geometrically of those two little triangles. I did show you how you could do it without using the graph by remembering that an absolute value function, this is a line with a positive slope. So I would go from 1/2 of the function itself, 2x minus 1. This side is the opposite of the function 2x minus 1. So you'll notice I have the opposite of parentheses 2x minus 1 from 0 to 1/2. So I can do it algebraically or I can do it graphically. Let's see. Solve the following conditional equations. In letter A, I'm finding the antiderivative, and I'm setting it equal to 0 to solve for x. So when I find the antiderivative, I'll get t to the 4th over 4 minus 7t squared over 2, evaluated from -5 to 0, and that's supposed to equal 0. So when I substitute 0 in, I'll get, let's move this down. So upper bound substituted, I get 0 minus lower bound gives me 5 to the 4th is 625 over 4 minus -5 is 25 times 7, so that would be 175 over 2. Oh, that's at x, I'm sorry. Bad Mr. Jernigan. Right. So let's erase that. So So that gives me x to the fourth over 4 minus 7x squared over 2 equal to 0. I think I'm going to multiply everything by 4, so that'll give me x to the fourth minus 14x squared minus 625 plus 2 times 175, 10, 15, 350 equal to 0. And this is clearly, I'm going to use my calculator to solve this. So if you take a look at the answer sheet, okay, so there it is. When you clean it up, oh, actually it factors. I didn't realize it was going to factor, but you could use a calculator. This is to the point where I just worked it. I combined my like terms and actually found out that it is factorable. And I get plus or minus 5 as the value of x that makes that equation true. Let's see, the next one, similar type scenario. I'm not gonna do that one for you, but it would work the same way. We can take a look at the answers, and this one does say use your calculator. The first one was factorable. This one says use your calculator. Let's see the answer to that one. So same process. You're going to substitute the upper bound of k in the lower bound. You're going to get your equation, and you're going to solve it with a calculator. The next problem, the temperature in degrees T hours after 9 a.m. was modeled by the function. Find the average temperature during the 12-hour period. Find the average temperature. There's that key word. So we have to decide, do we need to move forward to find the average, or do we need to find the antiderivative? Well, if you take a look, let's look at the solution, then we'll go backwards and talk about it. Notice that we're finding the antiderivative, 1 over b minus a, from 0 to 12 of the function. Question, why are we doing that? Well, this is telling me to find the, you can almost substitute in here, find the average value of the temperature. So whenever you can substitute that term, the average value of the temperature, then you know you're going to use the average value formula. These can be a little bit confusing to try to figure out whether you need to move forward and find a derivative, or whether you need to move backwards and find an antiderivative. And hopefully, as we experience more of those, you'll feel better about them. Number 7, the table below gives the values for a continuous function. We want to use a left endpoint approximation with 6 subintervals from 20 to 50, and we want the average value. So when we're finding average value, we're going to go 1 over b minus a, so 1 over 50 minus 20, from 20 to 50 of f of x dx. So don't forget about that 1 over 30. That's going to be important. All right, so now we're going to have 1, 2, 3, 4, 5, 6. We're looking for a left endpoint approximation. All right, so the 1/30th is where I'm dividing by my time. That's 1 over b minus a. Now I need to find the area of my rectangles, and each rectangle, I believe, is 5 units. So we have 5, 5, so everything is by 5. So the common width of the rectangles is 5. Make sure they didn't try to trick me there. And then I'm going to multiply by the height, so I'm going to have the first left endpoint. Remember, the last one doesn't come into play, so I have 42 plus 38 plus 31 plus 29 plus 35 plus 48, which you can see that the answer on the answer sheet, let's see what it is, turns out to be 37 and 1/6. And then finally, number 8, find the numbers b such that the average value is equal to 2. Now, so I'm finding the average from 0 to b, so I have 1 over b minus 0 from 0 to b of 2 plus 6x minus 3x squared dx, and that answer is supposed to be equal to 2. So it's really the same kind of problem that we had earlier. I'm going to find the antiderivative, so I have 1 over b minus 0 times 2x plus 6x squared over 2, so it would be 3x squared minus 3x cubed over 3. So that would be minus x cubed evaluated from 0 to b equal to 2. So I'm going to have, well, 1 over b minus 0 is just 1 over b. And I'm going to actually multiply that b, this b to the other side, and so I'll have 2x plus 3x squared minus x cubed evaluated from 0 to b is equal to 2b. Again, I multiplied the b to the other side. So now I'm going to use fundamental theorem of calculus, so I have 2b plus 3b squared minus b cubed, that's upper bound. Substituting in the lower bound will give me 0, and that's equal to 2b. So the 2b's are going to subtract out, so I get 3b squared minus b cubed. I can factor out a b squared, and that'll leave me with 3 minus b equal to 0. So b is equal to 0, or b is equal to 3. All right, and we're looking for, let's see, just verify, yep. B equal to 0 doesn't work because we're looking for a value inside of the interval, and 0 is one of the endpoints. I mean, 0 is the first endpoint, so it's not, we don't have to worry about it. B was the other endpoint that we were looking for. Hopefully this helps. If not, come in, ask more questions. Be glad to help you.